Welcome to This Explainer. Have you ever stared up at a massive skyscraper or driven across a sprawling suspension bridge and just wondered, how on earth did this get built without everything turning into absolute chaos? Well, today we're taking a look behind the curtain of these massive engineering operations. We're going to uncover exactly how an idea goes from a simple blueprint to a physical reality by exploring the precise frameworks that keep these giant undertakings on track. It really is a fascinating puzzle. Think about it. How does a multi-million-dollar project with countless moving parts, dozens of specialized teams, and literally millions of dollars on the line actually get finished on time and on budget? The secret lies in a really beautiful contrast. It's about taming the absolute chaos of human coordination with the pure mathematical elegance of ordered dependencies and rigorous scheduling. To figure out how this is done, we'll hit 5 key areas today. First, the foundations of who and what. Second, the RACI matrix. Third, building the network. Fourth, time and money. And finally, finding the critical path. Let's kick things off with section 1, foundations, the who and the what. Okay, before a single shovel ever hits the dirt, we absolutely have to know where the money is coming from. The source material highlights a really stark contrast here. If you're working on a public project, say highways or schools, it's funded by taxes or bonds. Because it's public money, it comes with incredibly strict procurement and change order rules. On the flip side, private projects actually make up roughly 70 to 80% of the total construction volume. They run on existing capital or loans, which means the project sponsor carries a whole lot more of their own direct financing risk. Once the funding is secured, how do we actually map out the build? Well, the source introduces a brilliant mental model for this, the Work Breakdown Structure, or WBS. Let's think about something simple, like a bicycle. A WBS takes the final product and simply splits it into major deliverables. You've got your frame, the gears, the wheels, the brakes. Then it breaks those major parts down even further into individual work packages, like the actual tires and spokes. It basically takes one big, intimidating idea and chops it up into super manageable pieces. Now, if you scale that exact same bicycle logic up to a complex construction project, it looks something like this. The massive master project sits right at the top, and it naturally splits into distinct phases: site prep, structural steel, brickwork, interior finishes. This matters so much because turning a massive skyscraper into highly detailed, bite-sized packages is quite literally the only way a manager can accurately track progress and spot a problem before it completely blows up the budget. Moving right along to section 2, the RACI matrix. So, we know what needs to be built, but who's actually doing it? To avoid that dreaded confusion over who is really in charge, we use the RACI framework. It defines roles perfectly. R stands for responsible. That's the person actually doing the work. Every single task needs at least one R. A is accountable, the person who ultimately answers to the project manager. Crucially, there should be exactly one A per task. Then we have C for consulted, meaning they provide two-way input and expertise. And finally, I for informed. They aren't doing the work, but they definitely need to be kept in the loop. Let's see how this plays out in practice. You've got tasks like assess risk or execute construction running down the side, and across the top, we've got the human element: project manager, consultant, architect, contractor, and client. By mapping these tasks and people together, we make sure every single task has an accountable party and a responsible worker. Take execute construction, for example. The contractor is the R. They're the ones literally swinging the hammers. But the project manager is the A. They're the one who has to answer for it if the deadline is missed. It essentially hardwires accountability straight into the system and removes any ambiguity.
All right, section 3, building the network.
Now that we have our tasks and our people, we need a solid order of operations. To connect all these isolated tasks into a logical flow, we rely on Hinz's 8-step process for developing a network model. It walks you step by step from defining activities all the way to calculating times and identifying the critical path. But keep in mind, this is rarely a strictly straight line. It's actually a continuous loop, mainly because reality never perfectly matches the blueprint. You plan, you draft, and you're constantly revising as conditions on the ground inevitably change. When it comes to ordering these activities, planners can easily get bogged down trying to figure out what precedes a task, what follows it, and what happens to run at the exact same time. But our source gives us a brilliant shortcut, the IPA, or immediately preceding activity. To use it, you just answer one single question for every task. What activities must finish immediately before this one can start?
Once you nail down the IPAs, the entire complex network practically builds itself. And here's what that logic actually looks like when mapped out for a basic concrete footing package. We draw the activities as nodes, and we connect them with logic lines based directly on those IPAs. Take activity D, place concrete. You obviously can't pour wet concrete until the steel reinforcement is fully placed, right? So the logic line flows directly from G to D. It creates a clear visual map of exactly how the work has to progress. That brings us to section 4, time and money. We've got our visual map, sure, but a schedule isn't really a schedule without timeframes. And estimating duration is, honestly, often more art than science. It's based on things like resource productivity, historical data, and overhead limits. Overhead is super interesting because it splits into job overhead, like renting a site trailer, and home office overhead, which is the company's general running cost allocated by the project's value percentage. All of these financial realities put constant constraints on how long an activity can logically take. In fact, sometimes duration isn't set by how fast a crew can physically work, but strictly by the budget itself. Imagine you have a hand excavation task budgeted at $950, and your crew costs $33.20 an hour. Divide the total budget by that hourly cost, and you hit a hard stop at roughly 28.6 hours. Literally, at 28 hours and 36 minutes, you have to tell the crew to drop their shovels. If they work a single minute longer, the project starts bleeding money. When we take those time limits and map them into every node in our concrete network model, we suddenly have the data we need to predict the future of the project. We've now added a D value, for duration in days, to each box. Activity A takes 5 days, activity B takes 8 days, and so on. Now we are finally ready to calculate the total time this entire project is going to take. Which leads us to our final section, section 5, finding the critical path. This right here is the absolute core of project scheduling. This is where all our foundations, logic, and durations finally collide. We start by calculating what's known as a forward pass. We slowly move from left to right through the network. You take the early start time, add the duration, and boom, you discover the early finish time. Look at activity B. The earliest it can start is day 5. The work itself takes 8 days. 5 plus 8 means its early finish is day 13. We just ripple this basic math step by step all the way to the end to find the absolute earliest possible completion date. Next up, we calculate total float. You can think of total float as your project's built-in shock absorber. It's simply the late start minus the early start. In everyday terms, it's the amount of buffer an activity has. It tells you the exact number of days a specific task can completely stall out before it forces the entire project's completion date to get pushed back. To find that float, we do a backward pass. We literally start at the final day of the project and work in reverse, subtracting durations to find the absolute latest a task can start without causing a delay. When the dust settles, you'll uncover a chain of activities with exactly 0 total float. This is your critical path. Because these tasks have 0 float, a delay in any one of them will directly and immediately delay the entire project, which we can now see clocks in at exactly 23 days. Now, a lot of managers out there rely really heavily on major milestones to track their progress. But the source text points out a completely fascinating limitation. Milestones usually track only the critical path. Sure, they tell you if those 0 float activities are on time, but they don't necessarily give you the true health of the overall project. You could be hitting every single milestone perfectly, while an absolute disaster is quietly brewing off the critical path. Which leads us to a really provocative question straight from the lecture notes to wrap up our explainer today. If milestones only show critical path progress, how would you catch a non-critical activity quietly slipping? Because think about it, if a non-critical activity slips past its total float, it suddenly becomes the new critical path, and your whole schedule blows up without any warning. It's a vital reminder that a master project manager has to watch the whole network, not just the red line. Thanks so much for joining me, and keep questioning how the chaos is tamed.